Oh, good evening. So can we get started?
Yes, sir. Good evening, sir. We can start, sir.
So in the yesterday's class, we have left here where the concept of polycrystalline materials and a single crystal material has been introduced, right? So for example, if you have a liquid pool, normally when the solidification happens, you will have some nucleation, and each nucleation site will be the site for a grain formation, and depending upon the random orientation that a particular unit cell has been created at that particular location, you may have different orientations. For example, this crystal is oriented like that, and this crystal is oriented at an angle 45 degrees to this. Okay. And similarly, there is this grain oriented in a different way. Each of them are oriented differently. And when they grow, when the grains grow in size, eventually there will be an incompatibility, meaning the unit cell edges are not matching. And as a result, this is one crystal, I can say this is another grain, it is another grain. There is an incompatibility at the grain, the boundaries of these grains, which are typically referred to as grain boundaries. Okay. So in a polycrystalline material, what you will have is these individual grains, each with a particular orientation. When I say, what do I mean by orientation? For example, we have looked at in yesterday's class at length about the crystallographic planes. Let us say this is my 111 plane of this crystal oriented this way, and 100 plane is oriented this way for this particular crystal. That means each grain is oriented in a different crystallographic direction. And because they are oriented in different crystallographic directions in that particular plane, at the intersection, you have incompatibility. So that is what you will see in a polycrystalline material. Is that point clear?
Yes, sir.
So now let us go back and think about the single crystal material. Okay. So in a single crystal material, we said, let us say, let us talk about a scenario. Let me reshare my screen once with the advanced sharing options. So now you can see there are different crystallographic planes I will show. So let us look at this particular crystal. This is our 111 plane, correct? And if I look at this particular plane, what is that plane? Zero 1 0 plane, correct? This is our 0 1 0 plane. Now, you know that the planar density on 0 1 0 plane is different from the planar density on 111 plane. Since the planar densities are different, let us imagine, that means the number of atoms sitting on that plane are different. Let us imagine if this is 111 plane and this is another 111 plane. Now, if I am pulling them apart, the number of atoms participating in the bond. So that means imagine these like a springs, atoms like a springs. Then the amount of resistance offered by this deformation, right, is going to be something. But instead of that, this is 100 plane, 100 plane. This is 111 plane and 111 plane. When I am pulling in this direction, the amount of resistance offered to the deformation, will it be same or different?
Different.
Different, because the planar densities themselves are different. And that means the resistance to deformation depends on the direction of your loading. In the case of a unit cell, a crystalline material, a unit cell if you take. And if you talk about all these unit cells are oriented in the same fashion, that will form a single grain. And that is what, if there are no incompatibilities in terms of orientations, then such a system is called a single crystal material. Meaning, if so, here this is a polycrystalline material. But if there is no such orientation issues, then this will not have any grain boundaries. Everything will be a single crystal material. Okay. So if you have a single crystal material, now depending upon the orientation you choose to deform the material, you will get different response of the material. That means the directional dependent properties come into picture. And hence, a single crystal material by its nature is an anisotropic material. By geometry itself, a single crystal material is anisotropic. As we have seen, the planar densities and the linear densities across different directions and different planes will be very different in a single crystal material. Now let us come to polycrystalline material. What happens in polycrystalline materials is that these grain orientations, there are so many grains and all these grains are randomly oriented. Because they are randomly oriented, in an average sense, the dependence of this directional property goes away. Because how these grains are oriented, nobody knows. There is no particular orientational uniformity here. Each grain is oriented in its own way, and as a result, you will not observe anisotropy, and hence polycrystalline materials are in general isotropic. That is the reason why when you do a uniaxial tension test on a mild steel, polycrystalline mild steel specimen, irrespective, you don't ask in which direction you have loaded the specimen. The elastic modulus is 210 GPa without asking any questions, because it's a polycrystalline material. The directional dependency will go away. It's on an average, it cancels out. And that is the reason why you have an isotropic property for that system. However, if you have a single crystal material, then it will never be isotropic. You have to pay attention to whether in which direction you are loading the system. For example, you look at this fellow. Here we are showing the properties of elastic modulus for aluminum, copper, iron, and tungsten when they are loaded in different crystallographic directions. So suppose if you are loading this material in 100 direction, 110 direction, 111 direction. Depending upon the direction in which you are loading, your elastic modulus measured will be different. For example, if you take iron, in 100 it is very compliant, whereas in 110 and 111 it is not that compliant. For aluminum, although there is some difference, the difference is much less. Tungsten, in these three directions, it does not show any difference. Maybe in some other direction it shows, but tungsten does not show any difference. So that means the depending upon the only three directions you have chosen, but there may be several other directions in which tungsten shows anisotropy. Okay. So that is an important observation or important feature that we need to keep in mind when we are analyzing deformation in materials. Any questions here? All right. Now, let me quickly go through. I will not spend too much time. Let me, in 5 minutes, we would like to finish this module. So, how do we know a material, whether it is FCC, BCC, or HCP? How do we identify this? Meaning, a material atoms are arranged in which fashion? How do we identify? Experimentally, how do you find out? The experimental way of finding this is through a technique called X-ray diffraction. Why X-ray diffraction? Because X-rays are having an appropriate wavelength so that they can probe the dimensions at this length scales that are of interest in order to find the crystal structure. Here in this picture, you see different waves, types of waves and their wavelengths. So you have radio waves which have very large wavelength and that travel over large distances, microwave, infrared waves, visible ray, and X-ray. If you carefully look at the X-ray wavelength, it is 10 power minus 10 meters. That means it is of the order of 1 angstrom unit, right? That is at the atomic level, and hence X-rays will be able to resolve the distances at that scale. And as that is precisely the reason why we are able to measure the crystal structure, the distances between the plane of atoms, which are at the level of few tens of angstroms. We are able to measure that. That is why people use X-rays for measurement of crystal structure. So how does this work? This basically works on a principle called diffraction, which we probably all of us have studied. What is the diffraction? It happens when a particular wave, a light wave, hits a regularly spaced obstacles. And the spacing, the diffraction occurs when the spacing is of the same order as the wavelength of the incident wave. That is why if you are interested in having diffraction, then you should choose the light of specific wavelength such that the wavelength matches with the spacing between the atoms. Spacing between the atoms is of the order of tens of angstrom units or a couple of angstrom units, and hence you need to choose a light of wavelength of similar value. And that is the reason why X-rays play a critical role. X-rays show a similar wavelength. And you need to have an obstacle that is capable of scattering the light. Okay. So now let us look at what's happening here. Suppose let us say you have an X-ray, two X-rays, a wave 1 and wave 2. When they are in phase, then you have something called a constructive interference, and then there will be increase in the amplitude. The amplitude A and A, then becomes it is 2A. But let us imagine a scenario, you have wave 3 and wave 4. So initially what is happening, you carefully observe here. You have wave 1 and wave 2, and there is a scattering event. Basically that means it hits an obstacle. After hitting the obstacle, again they maintain the phase. If they maintain the phase, then you will see a constructive interference. Now you are sending the wave at the scattering event. When they hit the atoms, then the resultant diffracted wave, if they have phase difference like that, then if you have out of phase, 100% out of phase, then when both of them meet, then you have an out of phase, and then there will be destructive interference. That means your wave signal will be completely lost. This is something that we already know. Now let us look at this picture. So whenever you have a constructive interference that is taking place, let us say this is wave 1 and that is wave 2. This wave 1 is going and hitting atom P. Wave 2 is hitting atom Q. And imagine the distance between, so this is a plane of atoms A and atom B. Then let us say this is 100 plane. All parallel planes will have same indices, right? So let us say this guy is hitting an atom on 100 plane, and then it diffracts in this way. Similarly, another atom which is hitting another light ray, X-ray, which is hitting another atom in the plane B dash, which is separated by a distance DHKL. This DHKL is what? Interplanar distance between two successive atoms, plane of atoms, whose indices are HKL. The plane index is HKL. Then the interplanar distance is described by DHKL. Okay. Then let us say this is incidenting at an angle theta. And the fact that the light ray 1, before it hits, it travels shorter distance, whereas light ray 2 is required to travel this much additional distance as Q. Right? The total additional distance traveled by light ray 2 is SQ plus QT. And if the path length difference, that is SQ plus QT, is an integer multiple of wavelength, then you will have constructive interference. If it does not, then you will not have constructive interference. Okay. All right. So the extra distance, so that now the additional path length that it has traveled is SQ by QT. And now this is basically n times lambda, that is lambda is the wavelength, that is the integer multiples of wavelength. N is your integer multiple of wavelength will be SQ plus QT. That is only when you will have constructive interference. And what is SQ? Let us say this is DHKL and this angle is theta. Then SQ is DHKL cos DHKL sin theta, right? And QT is also DHKL sin theta. So you have n lambda is equal to 2 DHKL sin theta. So that is what we popularly remember, n lambda is equal to 2d sin theta. What is d here? Interplanar spacing between those two planes of atoms. Okay. So this technique of X-ray diffraction was invented by these two Nobel Prize winners. Both are William Bragg and Henry Bragg. Both of them are Nobel Prize winners, father-son duo, who won Nobel Prize for determining crystal structures using X-ray diffraction. And he is, at that time, he was the youngest Nobel Prize winner in science. So the interplanar distance is given by, for a cubic system, is this formula, where A is the lattice parameter, H, K, L are the Miller indices for that particular plane. That gives you the interplanar spacing. Okay. So A is the lattice constant, H, K, L are Miller indices. So what we have said, n lambda is equal to 2d sin theta. D is A by square root of H square plus K square plus L square sin theta. Then lambda by 2a. Yeah, let us say n equal to 1 for n equal to 1. N equal to 1 is what we call order of diffraction. If n is equal to 2, then means order of diffraction is 2. N equal to 3, order of diffraction is 3. That means how many integer multiples of lambda is SQ plus QT. So let us say n equal to 1, then this becomes lambda by 2a is equal to sin theta by root H square plus K square plus L square. If you take square on both sides, then you have sin square theta by H square plus K square plus L square. So now when you are doing the X-ray measurement, you know what is the incident wave length of the X-ray that you are using. So lambda is known, right? And from the experiment, if you find the theta's diffraction angle, then you will be able to find out the interplanar, so the atom size, whatever you are talking about. Okay, so I am not going into the details. So this is how an X-ray diffraction experiment is done. This is a diffractometer. You will put a sample and then send the X-ray. So this is C is the detector, and this is X-ray source. From here, X-ray will be sent, and then it gets diffracted at an angle theta, and then this will be 2 theta. And then by measuring this fellow, you will get a signal something like that. So diffracted angle 2 theta and intensity, you will have peaks corresponding to particular planar indices, Miller indices. Depending upon the type of crystal structure, you will know where the peak will occur. If it is a polycrystalline alpha iron, you should have a peak at 110, 200. 110 peak will happen at 45 degrees. 200 peak will be happening at 65 degrees. So this is how your diffraction pattern looks like. By looking at this diffraction pattern, people will identify what type of crystal structure that the material has. Okay. So let us look at, so this is the polycrystalline alpha iron, and let us try to find out what is the diffraction angle, right? So DHKL, see, let us say that for BCC iron, we need to compute the interplanar spacing, the diffraction angle for 220. So DHKL is what we need to find out, interplanar spacing. That is A by square root of H square plus K square plus L square. All right. The lattice parameter is for the iron is given 0.2866. And for this particular plane, you can calculate interplanar spacing is 0.1013. And corresponding to this interplanar spacing, what should be the diffraction angle? Theta should be 62.13 degrees. Then 2 theta should be 124.26. So you will have, if you go forward, you will see at 124.26 a diffraction, a peak at that particular angle. So that's how you can calculate that where will be the peak happening for that particular set of planes and the knowing the lattice parameter of the structure. Or if you know what this guy is, you can also back calculate the crystal structure. But let us not worry about at this point of time, because in this class the focus is not on how to get the crystal structure, but I'm just telling you these things so that you know that there is a way to compute or identify the crystal structure if we know the lattice parameters and planar, what is the planar, interplanar spacing and so on. Okay? Any questions here?
Clear, sir.
All right, so we are done with the crystal structure. Now we will talk about something called imperfections in solids. Okay? So why do we need to talk about this? So we know until now what we have studied is that in a crystalline material, the atoms are arranged in a regular manner with long range order. That is what we have learned so far. But in reality, what happens is, will this long range order exist or will there be any violations? And if there are violations, what kind of violations will be there? And that is something that we need to study. And if there are violations, which we call as imperfections, if at all there are imperfections in this material, in these crystalline materials, what should be what is the effect of these imperfections on the deformation mechanism or on the deformation behavior of the materials? So these are the questions that we would like to address now. Okay. So in this module, what we will learn is what are the different types of defects in a solid, and we will try to calculate the equilibrium number of vacancies in a material, which is number of point defects, and then different types of solid solutions and what type of line defects. We will talk about dislocations and so on. Okay. So maybe I will move on. Again, when I need my iPad, I will bring it, but otherwise I will go with Now you're able to see the screen, right?
Yes, sir.
Yes, sir.
Yeah. So now what we will do is we will try to list different types of defects, and then we'll try to calculate the equilibrium number of vacancies in a material. What do I mean by that? I will describe in a moment's time. So the question is, do we have perfect crystals? Do we have a crystal that has long range order everywhere? And it turns out that unfortunately there is nothing called perfect. You cannot find a perfect crystal. Whenever I ask this question, can you name some perfect crystals? Several students tend to answer that as diamond as a perfect crystal. Okay. Even although diamond is expensive, does not mean that it is perfect. There are so many defects in diamond. Okay. So defects are part and parcel of any crystalline material. Okay. And many times nature does not seek perfection. Nature actually wants imperfection because it can do several good things too. Always we see defects as something that is bad, but sometimes defects can be good too. So what are these useful imperfections? If you look at metals, right? Most of the useful metals are alloys. What do you mean by an alloy? Alloy means adding a foreign atom to a parent atom. That means we are a pure metal, otherwise a pure metal is impurified. Right? You are adding impurities to the parent atom. That is actually introducing defects in the otherwise perfect crystal. And that is an advantage because several alloys are much stronger than their unalloyed counterparts. And hence, alloys gives the desired properties by actually introducing imperfections. Similarly, semiconductors, you add dopants, which is an imperfection, which will help us work with electronics today. So if it is not for imperfections, we would not have made so much of progress in science as of today. So now so how do I define a crystalline defect? What is a crystalline defect? It is simply a lattice irregularity, meaning you expect, whenever you say a lattice, you expect some positions to be filled by atoms in a specific manner. That is what you mean a crystal is. All right. If whatever is supposed to be there is not there, then that is considered as a lattice irregularity or a crystalline defect. So it could be at various dimensions. It is simply a missing of an atom or presence of a foreign atom which is not supposed to be sitting there. All these things are defects. And typically the classification of these defects is based on geometry and dimensionality. So what do we mean by that? So the first class of defects are called point defects. So let us say this open circles is your otherwise perfect crystal. And in that, this big guy is a foreign atom, which is actually sitting in the place where this open atoms should be sitting. But this is a larger atom, which is substituting in the position of an open atom. And that is a defect actually, right? So this is what we call a substitutional larger atom. And if you look at this position, you expect to see an atom here, but there is no atom. So that is also a lack of an atom is also a defect, and that kind of a defect is called a vacancy. Now, if you look at this position, in this position, you don't expect to see an atom, but you are actually seeing this atom. So that means at an interstitial location, meaning interstitial location means that somewhere between these atoms, you are not supposed to see this guy, but it is sitting. So that's an interstitial defect. Here at a substitutional location, you have an atom which is smaller than the original atom. So that is a substitutional smaller atom. And this is an interesting thing. Here you should have an atom, but it is not there. So there is a vacancy here. But in the neighborhood of that vacancy, you have an interstitial atom. So you could see this. You can imagine this guy as this atom, which is supposed to be sitting there, is sitting here. So this is one defect, this is one defect. These together is considered as a pair, which is called a Frankel pair. if the distance between a vacancy and the interstitial atom is only one atom in interplanar spacing, then you can consider as Frankel pair. Is that clear? So these are all point defects, basically presence of an atom or absence of an atom in a place where it is not supposed to be there. And so these, so for example, if you have an ionic crystal, so like sodium chloride, so you have to have an Na plus atom and chlorine minus, and you can see that here chlorine, sodium atom should be sitting, but it is going and sitting in an interstitial location. That is why it is called Frankel pair, Frankel defect. And here you will see that here you have to have a chlorine atom, and here you have to have a sodium atom. Both of them are missing, and hence this one is called Schottky defect. That means net charge is remaining 0 for the structure because both the atoms of opposite sign are missing. Such a defect is called a Schottky defect. Okay, so these are typically observed in ceramics and intermetallics where charged atoms are sitting there. But all of them are point defects. So whenever you have a point defect, how do we create point defects? Basically by providing thermal energy. You create thermal energy, then the atoms, instead of vibrating in their equilibrium positions, because of higher energies are supplied, the atoms go from their equilibrium position to somewhere else. That is why you have, by thermal activation, you can create point defects. And when you create a point defect, it increases the internal energy of the crystal, isn't it? Because you are increasing the energy, thermal energy. So the internal energy of the system is increasing. Now, we know what does nature try to do? Always? What nature tries to do? Does it try to minimize energy or maximize energy?
Balance the energy.
Huh?
Balance
Minimize.
the energy.
What do you mean by balance the energy?
Minimize ground state. Return back to ground state.
Ground state. But if presence of a defect is going to increase its internal energy, then nature should not create point defects, right? Because it is against principle in which the nature operates. Then the question is, why nature allows the creation of the point defects is the question that we have to answer. The answer lies in here. The reason why crystals create vacancies or point defects is because it happens as a consequence of competition between entropy and energy, or competition between probability and energy. What do we mean by that? In order to understand this, let us carefully understand this concept of vacancy formation energy. What do you mean by vacancy formation energy? It is the amount of energy that is required to create one vacancy in a crystal. That means you have a crystal. Suppose you have a crystal, in this atom is there. If I have to move this atom from this position out of its crystalline location outside this crystal, I need to spend some energy, isn't it? That energy is what we call vacancy formation energy. Okay, so let us now assume that the crystal is in equilibrium with vacuum. And now the relocation of an atom from its lattice side to external surface. External surface, if you bring, then it is leaving the system. Creates, what happens? You will create a local distortion causing the increase in energy. What do we mean by that? If I remove an atom from here to surface, what will happen? Until then, this locally, this system, so for example, I am removing this atom. Are you able to see my mouse?
Yes, sir.
Yeah.
Yes, sir.
If I am removing this atom, right now these are at certain equilibrium state. The moment I remove atoms, I am actually breaking these bonds. Then what happens? There will be local distortion. These atoms will move because now, until now, this atom is not letting this guy to move in this way because of the equilibrium spacing between them. Now, these atoms will relax. This atom will move this way, this atom will move this way, and so on. That means you are creating a local distortion in the crystal, isn't it? And that will cause increase in the internal energy of the system. And that energy is what we call vacancy formation energy. And now, if you create these vacancies, continue to create these vacancies, then you will be able to move all the atoms from the material to the vacuum, because you are actually in equilibrium with vacuum. So we know that complete segregation of atoms and vacuums is not possible. Now, what happens? That means there is a competition between the vacancy formation energy and the probability that determines the equilibrium vacancy concentration. What do we mean by that? So the number of vacancies in a crystal is given by this expression, n e power e minus ef by kT. And how do we get this expression is what we will see. Let us say you have nv number of vacancies in an atom, in a crystal. So you have so many atoms, right? In these so many atoms, there is one vacancy here, another vacancy here, and so on. If you count all those number of vacancies, let us say you have number of vacancies in a crystal or NV. And the number of atoms in a crystal are Na. And Na plus Nv is number of lattice positions. Ideally, each lattice position should be occupied by a atom. But because not all the positions are occupied by atoms, you only have Na atoms and Nv atom vacancies. Nv plus Na will be total number of lattice sites. Is that clear?
Yes, sir.
Yes, sir.
Now, typically, the number of vacancies in a crystal should be much, much smaller than the number of atoms. Otherwise, you will only have open space, not materials in reality. So, because in nature we don't see open space all the way, you have materials. We are talking about vacancies inside the material. Nv by Nev should be much, much less than 1. That means the number of vacancies should be much smaller in number. Okay. Now, in order to create a vacancy, we have discussed the amount of energy required for creation of a vacancy is what is called a vacancy formation energy, EF. If I have NV vacancies, then the total energy of the crystal increases by this much amount, NV times EF. That is the U. And EF is always to be positive, because if it is negative, that means you don't need, by creation of vacancy gives out energy. But creation of vacancy requires energy, and hence it should be positive. Okay. And what happens is in crystals, they allow vacancies to increase entropy. What is entropy? Entropy is a disorder of the system. A perfect crystal is an ordered system. What crystals do is they allow vacancies so that the entropy of the system can increase. So the entropy of the system can be written by K log W. What is W here? W is the number of ways we can arrange NV vacancies in these many atom sites. How many vacancies, how many ways that I can create vacancies in these many total number of lattice points, lattice sites. So that is given by, this is the probability, NV plus Na factorial by NV factorial Na cofactorial. Now we know the total free energy of the system is internal energy minus T times S, where S is the entropy. And thermodynamic equilibrium requires that whenever you are creating a variation through these vacancies, the dH by dV is equal to 0 means the minimization of the free energy. It is not that the nature tries to minimize the internal energy. What nature tries to do is to minimize the free energy. How do I minimize the free energy? By minimizing the internal energy or maximizing the entropy. You can actually have you can minimize the internal energy by increasing the entropy, increasing the internal energy, and increasing the entropy. If you increase the entropy at a much higher rate than increasing the internal energy, then the free energy reduces, isn't it? So that is the logic here. It is a competition between energy and entropy. So the minimum value is reached when dH by dNv is equal to 0. So let us plug that in. log W. So because S is what? K log W. Log W is this. If you would plot log of a function, that is the red curve, and that can actually be when this value of x is much, much larger, then that can be represented by x log x minus x, this green curve. For much larger values of x, a log x factorial is equal to x log x minus x. Meaning, I can say log x factorial can be replaced by x log x minus x. So I can then write log a by b is log a minus log b. Log a is log nv plus na factorial, can be written as nv plus na times log nv plus na. Similarly, log nv factorial, log na factorial, log a log b is equal to log a plus log b. And again, nv and log nv and na nb. So here I have applied Stirling's approximation to this particular formula to write what is my S. This is what we call entropy of mixing, where Na is the number of atom sites, number of atoms, Nv is the number of vacancies. And now I plug in U is equal to Ef times Nv minus Ts. Now if I find the derivative of dH by dNv equal to 0, then I have Nv divided by Na plus Nv. Na plus Nv is the total number of lattice sites that I can represent with capital N. So Nv is equal to N times e power minus Ef by Kt. That is the equation that we have seen here. N is the total number of lattice sites. So what this equation tells us? This equation tells us the number of vacancies in a crystal with these number of lattice sites will be depending on vacancy formation energy and the temperature of the crystal. When will be this quantity be 0? Nv will be 0 when?
EF is 0 or T is very high.
T is very high. Is that true?
No, EF is 0.
EF is equal to 0. What will happen?
It becomes
The
1.
thing in equilibrium.
No. See, Nv is equal to N times e power minus Ef by Kt, isn't it? That is the formula. N is the total number of lattice sites. If Ef is equal to 0, then what happens?
It tends to 1 actually.
Yeah,
So
Ef is equal to 0 means e power 1.
EF
power
should be
0,
high.
1.
EF should go high actually then.
Yeah, but Ef should be infinity,
Yes, yes.
right? That means it should be extremely difficult to create a vacancy. Then only number of vacancies will be 0. Agreed? Yes or no?
Yeah, logical, sir.
Yeah.
So log-
But
Yes,
having
sir.
an infinite, the energy is not meaningful. And what is the other extreme about the temperature? At what temperature Nv will become 0?
0.
When absolute temperature T is equal to 0. Otherwise, for any finite temperature, for any finite value of Ef, where K is a Boltzmann constant, you will always have some vacancies in your crystal. Right? This is what we call an equilibrium concentration of vacancies. Even if you take any material, depending upon the temperature at which you are operating, that material will have some vacancies. Those vacancies are calculated by this formula. Is that clear? You cannot have a crystal which will have 0 vacancies, because 0 vacancies are possible only when absolute temperature is 0. Can we reach absolute temperature 0?
Cryogenics.
Cryogenics will let you go to 0 Kelvin.
No, sir, not possible practically.
Thermodynamics breaks down, right? Thermodynamics tells you that it is not possible to reach absolute 0. Right?
Yeah, right, sir.
Nobody can approach absolute 0. If you go to absolute 0, then Nv is 0, but it is not possible. So no, there will be absolutely no crystal without any defects because of this. So now let us do this. Let us look at this problem. Okay. Calculate the equilibrium concentration of vacancies per cubic meter of copper at 1000 degrees C. Okay. The energy for vacancy formation is 0.9 electron volt per atom. The atomic weight and density of copper at the above temperature are 63.5 gram per mole and 8.4 gram per cc. And Boltzmann constant is 8.60 into 10 power minus 5 electron volt per atom. So if I know the theoretical density of copper, so I can find out what are the number of atom sites. All right, the number of atom sites is Avogadro's number times density divided by atomic weight of copper. We have calculated theoretical density. The theoretical density is 8.4 gram per cc. Then in a cubic meter of copper, you will have 8 into 10 power 28 atoms. Can you imagine this number? Huh?
It is very high, sir.
Very high. Can you imagine what is this number?
Sir, can just display the number 1 second, please, if it's a request.
I'm showing you.
Maybe a mountain of copper.
Is it a mountain of copper?
It's just 1 meter cube of copper having this many atoms, so they are closely packed out.
It is only 1 meter cube of copper, isn't it? It's
Oh,
not mountain
sorry.
of copper. Those many in cubic meter of copper.
Oh, per meter cube. Sorry.
Yeah.
Sorry.
Yeah. So 8 into 10 power 28. We have in the universe, we have around 2 trillion galaxies. Right? And that before that number, the 2 trillion galaxies look very small before this number, isn't it? 8 into 10 power 28 is much larger number. So those many atoms are there packed in that. Okay. Now, in 8 into 10 power 28 atoms, how many vacancies are there if the copper is at 1000 degrees Celsius? And if you do that calculation, you get my 2.2 to 10 power 25 vacancies per cubic meter. So many vacancies, right? Why is there are so many vacancies? Because you are actually at melting temperature of copper close to. That is why no atom is sitting in equilibrium configuration. Now, can you calculate this number of vacancies at room temperature, say 30 degrees Celsius, and tell me what this number would be? EF is 0.9 electron volt per atom. K Boltzmann constant is 8.62 into 10 power minus 5 electron volt per atom Kelvin. 8.62 into 10 power minus 5 electron volt per atom Kelvin. That is the Boltzmann constant. Temperature instead of 1000, I would like you to calculate that for 30 degrees Celsius.
Sir, here, what is the unit in the temperature in this equation? It is in Kelvin, sir?
It is always in Kelvin, yes.
Oh.
Or is it 8.67 into 10 power 13?
So the number of vacancies have come down significantly, isn't it?
Yeah.
What is the percentage? Can you calculate the percentage? Number percentage of vacancies. What is the percentage? I would like you to calculate percentage of vacancies here and at 30 degrees Celsius and report.
Close to 50%.
Where, when, at this temperature?
At 30 degree.
At 30 degree, you have 50% vacancies, sir.
Yeah, I'm just going by the order. 10 power 13 and 10 power 25.
Mhm.
Like it's double.
It's almost 1 e power minus 12. E power minus 12 is a ratio. That much small.
E power minus 12.
Yes, 1 e power minus 12.
1 e power minus 12 percentage.
Yes.
Someone is saying how many number of vacancies are there at 30%, 30 degrees Celsius?
I got 8.67 into 10 power 13. But I would like to verify that with colleagues.
Okay. All right. So you please verify because I wanted you to get a feeling for these values. That is why I'm asking you to compute. If you are not computing, then I'm waiting for nothing. Okay. All right. So what is the effect of this point defect? So the point that I'm trying to drive here is that even at room temperature, you have so many vacancies in every crystal that you're talking about. So that means defects are part and parcel of your crystal structure. Okay. In your crystalline materials. Now, what is the effect of these point defects? So they can sometimes the defect concentration may result in different properties. Right? The properties of your material depends on the defect concentration, and the defect concentration can be influenced, can be increased or decreased by appropriate material processing. For example, you can increase the number of defects by quenching or flash deformation or irradiation, or rapid cooling from a melting point will not let the vacancies reduce. That means the number of defects will increase and so on. And as a result, if you quench a material, you will have more number of defects. As a result, you will have much higher strength to the material, but the ductility of the material gets reduced. So the mechanical properties are significantly influenced by the creation of point defects. That is one of the reasons why we should be worried about the point defects. And one of the main reasons why point defects are important to be looked at is because radiation damage is one of the very concerning process by which the point defects are created in materials, particularly in the nuclear industry. All right. What happens in a nuclear reactor? In the nuclear reactor, because of this chain reaction, you will create so many number of high energy neutrons, right? So these typically these are subjected to something called a neutron irradiation. So if an atom is going to receive some energy from the neutron, because the high energy neutron, so some high energy particle is coming and hitting an atom here, and if the energy is supplied to this particular position or any atom is greater than its vacancy formation energy, then what will happen? That atom will be moved from that crystalline lattice position. That is what it means. So the neutron irradiation, what it does is it primary collisions. When the neutron hits a particular atom, there will be some energy that is transferred. Because of that, because of that energy, when that energy is greater than the effective displacement energy or moving vacation formation energy, then the atom will be displaced. But if the energy is much higher, then the continuous cascading of this effect may happen. That means you hit a primary knock-on atom will come and hit this fellow, and that will create energy, and that goes and hits the secondary knock-on atom, and so on. That means the cascading of these events will take place, and as a result, you will create several defects in your crystal. And that is what typically observed in radiation damage in materials. So here we are showing a stress strain diagram for a zirconium alloy, ZIRC alloy, which is an unirradiated sample. That means when it is actually kept it in the radiation nuclear reactor before commission, but after it is getting irradiated for this much of dosage, 10 into 10 power 20 civets per centimeter square second, neutrons hitting it. Then what happened to the mechanical property? The material, which was otherwise having certain strength and a large ductility, has attained much higher strength, but became extremely brittle compared to this fellow. And that's a dangerous thing, because although the material is gaining strength, it is losing its ductility. So if at all it is going to break, it breaks suddenly, and that can be catastrophic. And hence, we need to be carefully monitoring the mechanical properties as a function of irradiation. That is why nuclear reactors are very critical, and people monitor the dosage that the materials are receiving from time to time and replace the materials when the dosage reaches some critical value. Okay. So, but that is a negative side of point defects, but point defects are also good in some sense. For example, ion implantation. So you can actually use this point defect creation in for preparation of the semiconductor devices, and sometimes you can actually use the creation of point defects to modify the surface chemistry. For example, you implant this bismuth plus nickel plus and molybdenum plus ions, positive ions, onto a steel, which will reduce the wear. So in order to reduce the wear, you can do the ion implantation on these things. Similarly, the oil burners are usually implanted with titanium and boron atoms through the point defect creation, which will improve their erosion properties. Okay. So sometimes you can actually have good sides of point defects, but point defects are also detrimental to mechanical properties of the materials. Any questions here? All right. Now, let us look at this concept of theoretical shear strength. Okay. Let us say you have a plane of atoms and below that you have another plane of atoms. Okay. Now you are applying a shear stress. That means you are sharing one plane of atoms past the another plane of atoms. The interplanar spacing is A. This is one plane of atom, another plane of atom. The interplanar spacing is A. You can also use D. Earlier we have used E, but here I am using A. Now, when the distance between two atoms is B, okay, and I am looking at three atoms A, B, and C. Okay. So whenever, so this is an equilibrium state. This is another equilibrium state. This is another equilibrium state. That is where the shear stress is becoming zero. That means when you are at this state is an equilibrium state. When you are increasing the shear stress, what happens? This atom moves past this, and it actually goes up the hill. And then, if you further want to move this to the right direction, you don't need to apply that much of amount of shear stress, because this is actually not going against the hill and it is coming down. So you will have initial increase in stress and then reduction in stress, right? And then you will have zero, and again you will fund. So you will have some sort of a sinusoidal function that describes the evolution of shear stress when you are sliding a perfectly crystalline material one over the other. If there are no defects here, right? All atoms are present wherever they are supposed to be present. And that can be represented by sine 2 pi x by b, where x is the shear displacement, b is the distance between two equilibrium positions, A and B. For very small displacement, we are actually talking about small displacement. Sine theta can be represented by theta. Yeah. Sorry.
Sorry to interrupt. How is that negative side of that this one is coming, sir, in the sine wave?
Yeah. So the shear, whether it is positive or negative, it is same, right?
Yes.
Yeah. So shear positive or negative direction is one and the same. So that is why you don't have to worry. You can you can represent this with the x is continuously increasing, but your shear is taking the negative sign. That's all. Okay.
Okay. Yes, thank you.
So a case sine 2 pi x by b can be represented by 2 pi x by b. Now you can write for all small displacements, material is deforming elastically. That means there is no plastic deformation whatsoever. Then the shear strain is represented by tau is equal to g times shear, tau shear stress is g times gamma. Gamma is your shear strain, right? So that gamma is basically angular strain, that is given by x by a, that is theta. This is x and that is a. You are talking about that that angle x by a. Tan theta is equal to x by a. So now you can write tau is equal to gx by a, then k can be written as gb by 2 pi a. So your shear stress can be written as gb by 2 pi a sine 2 pi x by b. For this, the maximum shear stress that the material experiences is gb by 2 pi a. Isn't it? Because sine 2 pi x by b can have a maximum value of 0, maximum value of 1. Right? So the maximum value of tau will be gb by 2 pi a.
Sir, but
this is the maximum shear strength of this material. If it crosses, so for example, if a point A is moving, this atom A is initially having a neighbors, this guy and this guy. Okay. Now, if this guy moves from here to here, it would have overcome this hill, isn't it? That means it would have overcome this gb by 2 pi a. And then this atom would have reached this position, which means this atom has changed its neighbors. Earlier, this atom has these two as its neighbors. Now, this atom has these two as its neighbors. The fact that it has completely changed its neighbors, that means that is a permanent deformation because its neighbors are completely changed. So, what we are saying is, this is the shear strength of the material to cause some one step of permanent deformation. That is gb by 2 pi a.
sir, I have doubt.
Yes.
Sir, will this change at different plane? due to the
Yes.
direction of loading.
Yes, in interplanar spacing, depending if it is a crystalline material, this has to change depending on the interplanar spacing. If you are talking about 100 planes, it will be something. If it is 111 planes, it will be something else because the interplanar spacing is different, as you can see from this formula. Correct?
Yes, sir. Thank you.
Now, let us look at an FCC material. Let us consider an FCC material with a lattice constant A0 and A and B. B is typically taken, this B interplanar, inter-atom spacing can be taken as A0 by root 2. Here A0 is the lattice parameter. And interplanar spacing D is given by A0 by square root of h square plus L, k square plus L square, where in this case, let us say we are interested in 111 plane of FCC material. Then this becomes A0 by root 3. This D111 is like our A here in this formula. This is our D111. If I plug that in, my maximum shear stress is coming out to be G by 5. That means the shear strength of an FCC material will be 1/5 of the shear modulus of that material. Here the shear strength is my shear yield strength of the material is as 1/5 of the shear modulus of the material. What is the shear modulus of, say, steel, for example? What is shear modulus of steel or elastic modulus of steel?
70 GPa.
Elastic modulus is 210, shear modulus will be 70 to 80 GPa. Correct? G is equal to E by 2 into 1 plus nu, nu is 0.3. So E by 2 into 1.3, that is 3.6. So 210 by 3.6 will be close to 60 GPa or so on. That is what it is. Right? If elastic modulus or shear modulus is 60 GPa, I am expecting my shear strength to be 6.6 GPa according to this. But what is the yield strength of steel, by the way? What is yield strength of steel? Do we know what is the yield strength of steel?
So for aluminum, it's around 45 kg per mm.
Yeah, can you tell me in your SI units? How come none of you know the yield strength of steel? You're all practicing engineers.
Sir, it is 200 MPa of order 200 MPa.
It is around 200 MPa. Depending upon the grade of steel, it may change, but it is a mild steel, it is 200 MPa. So it is in the order of megapascals, isn't it? But whatever calculation that we have done, it is actually giving you in the order of gigapascals. That means the strength that we have calculated using theoretical model is giving much higher strength than what is actually experimentally measured, isn't it? Experimentally measured values are few megapascals, who had tens or hundreds of megapascals, whereas theoretical shear strength that we are computing is of few gigapascals. That means there is a huge difference in terms of the computed value and the actual value. Now the question is, why is such a huge discrepancy? Why is that theoretical shear strength is so high while the real strength of the material is not that high? So the reason is the presence of the defects in materials. That is the reason why your shear strength of the material in reality is much less compared to theoretical strength that we have calculated. Okay, so when we have looked at the defects, so far we have looked at point defects. They are called zero-dimensional defects, point defects. So there are different length scales of defects. Here we have looked at atomic defects, point defects here. Much lower length scales, you have electronic point defects. That means number of, if you have a pure atom, the number of electrons is equal to number of protons, right? If an electron is missing, then that becomes an ion. Ion is an atom with defect, right? So that is what we mean by electronic point defects. But we have not looked at that. We have looked at the atomic point defects. But then the next level of defects are called line defects. That means you will have a defect in a line. And you also will have something called interfacial defects. They are called two-dimensional defects. And then we have volume defects. These are three-dimensional defects. From dimensionality, this is zero-dimensional defect, one-dimensional defect, two-dimensional defect, and three-dimensional defect. So whenever I am talking about zero-dimensional defect, I am talking at the level of angstrom units. Whenever I am talking about line defects, I am talking at the scale of microns. Whenever I am talking about interfacial defects, I am talking at the scale of a few microns to few centimeters. And volume defects, I am talking from few centimeters to sometimes tens of centimeters. Okay. That is the length scale that we are talking about. So what is a line defect? All right. So let us look at this particular video. Oops. This video is not working. So let me see. So these line defects are also called a crystalline defect, dislocations. In crystallography, these line defects are also called dislocations. And we have seen that the stress required to plastically deform a crystal is much less than the calculated for perfect crystal, as we have seen. So how does the concept that there should be defects in materials which are essentially line defects in order to explain the reduced shear strength than theoretical shear strength was conceptualized theoretically in 1930s by these people independently. Theoretically, they have figured out that there should be something called a line defect, but nobody saw a line defect until 1947. For 15 years, people only relied on theory that there should be something called line defect so that we can explain the concept of reduced shear strength, a lower value of shear strength that we measure experimentally compared to the calculation. And after 15 years, people were able to observe the line defects or dislocations under microscope. Okay, what do you mean by a line defect? Let us look at this fellow. You see, now let us look at the defects. So here you have, this is an experiment, which is a bubble raft experiment. What do you mean by a bubble raft experiment? It's very simple. Many times you would have done at home, when a kid you would have done, or your kids must be doing it. If you are married, your kids must be doing now. If you take a bucket of water, add some soap, and then mix it, then you will have a set of bubbles that form on the surface, isn't it? And now if you do a careful creation of those bubbles, this is such a bubble raft. Or you can also see these kind of bubble rafts. This is actually a bubble raft that is created on a surface surface on a bucket of water. But you can also see these kind of bubble rafts when that are coming in the packing materials. But doesn't matter. This is one such bubble raft which is created on a surface of water. When this is created, you can see some defects. So this is like an interstitial defect, point defect. And here you have another substitutional defect, and so on. And here, if you see, these are the different kinds of defects. Now, if you look at this guy, you see, if you look at this fellow, you have a line of atoms. For this guy, you have a line of atoms continuing. And for you, look at this fellow, the line of atoms continued up to here. After that, there is no line of atoms. Can you see that? This line of atoms are missing. Only there is a partial line and another line of atoms are missing. So the missing this line is called a line defect or dislocation. Is that clear?
Yes, sir.
Yeah. Now let me explain this concept a little bit more. Let us do this thought experiment. Okay. If you imagine you are sitting in a function hall, big function hall. In the function hall, you have set up, there is a carpet that is put on the function hall ground. Okay. Now, by mistake, people, the carpet should be starting from here, and let us say this white patch is the carpet. Okay. Now, instead of create what it should have happened is this carpet should actually have started here, but by mistake it started here. Then what you need to do? It's a very huge ground, and on this ground, this carpet has to be moved from here to here. How will you move it?
We'll pick the ends and pull.
By dragging.
We will drag it, right? So is one person will be able to do it?
No.
You need an army of people, isn't it? Because imagine this function hall is as big as say 20 meters by 20 meters. Right? So if this is 20 meters, then you need at least a couple of people to lift it and pull it, isn't it? Yes or no?
Yes, sir. Yes, sir.
Yeah. So that is how we can move it. Is there any other way? If you are only one person, you are required to do it, or you have only two people and you are required to do it.
Roll it and then roll it and then what I mean to say is do the further actions, whatever.
Exactly.
needed.
You completely roll it, move it, and unroll it. Correct? Yes.
Right, sir.
Agreed?
Seems to be the best option. Yes, sir.
Yeah.
Yeah.
What is the other one? Suppose you are not able to roll it. What is the other option?
Create a like what I mean to say is create a gap between the floor and the mat in such a way, like insert some what I meant to say cylindrical sticks, which can decrease the friction between the surface and this and then pull it off in that way.
But that will be, you have to put a gap throughout the mat, no?
Yeah, 2 and 3 at the beginning, and then if you roll it, it will just keep rolling in that way. Just a thought.
There is no provision for rolling.
Yeah, drag it in that way. That's what.
No, but
Spinning.
if you have to add some gap, no? You have to add that gap throughout the over the entire area.
Yeah, that's the problem. Yes.
That is the problem. Is there any other solution?
Sir, we can flutter and pull. That
How?
Flutter like move sinusoidally up and down and try to pull.
Okay.
Reduce the effort.
Yeah, to reduce the effort, you can do that. What is the other way?
We can
We can add some other carpet in the gaps.
Sorry?
Again,
Okay. So let me give you another idea.
Sir, one thing is that if the 4 person is there, they can simultaneously lift it at the 4 ends, and then probably they will be able to do it with lesser effort.
20 meter by 20 meter, very heavy carpet, no?
Yeah. Okay,
so
sir.
What if I create a sinusoidal a hump at one end? And so imagine I'm doing this, okay? Sorry, I'll just let me. This is my carpet, no? What if I do only I create this along that line? Okay. This creation is easy, no? Now what if I walk along this fellow? What will happen?
It will be moved a bit.
So I can keep walking. Then what will happen? This hump will keep moving, you know. You must have done this when there are not many people. At least I have done it in several functions. Then eventually you would have made a small step. And if you do it several times, you will be able to make progress. And you would have moved because you have done that, and then you are pushing this fellow with your feet. And then eventually you will move this thing. Here you will spend much less effort compared to taking this thing and moving it directly. Can you say, do you agree?
Yeah,
Yes,
fully
sir.
agree, sir. Fully agree.
Yeah. So now let us look at this animation, okay?
Just one question, sir. Whether
Yeah.
this trial was done by you before you have learned this concept, or at the childhood only?
I did it in childhood
Okay,
as a
cool.
kid because it is natural.
Okay.
Okay. Then I try to use that example now in the class. Okay. All right. So now let us look at this movie. What am I doing here? Can you carefully observe? This is exactly what we were discussing. You are moving, when you are moving the entire carpet, no? That means you are breaking all the bonds simultaneously and then recreating new bonds. If you carefully observe that when I am applying shearing, all these bonds are broken simultaneously and then they are recreated. Can you see that?
Yes, sir.
Right? This is what we mean by slip, by glide of plane of atoms. You are creating slip, and as a result, what is happening in this picture is initially you have a line defect here, and everywhere it is perfectly crystalline. And now I am moving. This is the step here, and at the end you will see that the step is created here. It appears as if the line defect which was here has moved here, isn't it? This is what we mean by creating a slip by glide of plane of atoms. That means all atoms in the plane are moved simultaneously. Now, how do I create? By dislocation motion, which is precisely what the example that I am talking about. I move one dislocation at a time, meaning I break it, and if you see what is happening, the entire thing is not happening simultaneously, but one atom. So you see that the red line I am moving because it appears as if a dislocation is moving from left to right, and eventually you got slip in this crystal. So this is what we mean by dislocation motion. That means the geometry position of the dislocation is moving, although the atoms are not significantly moving, right? So that if the position of the dislocation initially was here has moved. And in this process, what is happening is at a time, only one atom bond is broken below the dislocation and a new bond is formed. And when you are talking, this is what we mean by plastic deformation, because we are changing our neighbors by breaking the bonds permanently. Okay. And this is the mechanism that happens in materials when it is doing plastic deformation, because you don't need that much of energy. You can achieve with much less energy. That is why when you do the experiment, you measure the shear strength to be much less than what you would have observed in the theoretical calculation. Anyway, I'll stop it here. I know it may be a little confusing at this point of time to you, but in the next class, keep these thoughts in mind. And in the next class, we will get more clarity on the concept of dislocation motion. Okay?
Sure, sir.
Yeah. Thank you.
Thank you.
Any other
Sir,
questions?
Thank you.
Thank you.
Sir,
Yeah.
sir, instead of starting 5:30, is it possible to start at 5 o'clock, sir? Or class?
There is another class happening for another team because there are two batches, no, 23 and 24 batch. So the class is happening at 5 o'clock for them. Sometimes it may spill over up to 5:15. So to avoid this unnecessary clash, we moved it to 5:30. And we will try to close exactly at 7. I know today I went by 10 minutes extra.
No, sir. That's not a problem. For our class, it was closed at 4:45, 4:55. So we have to wait at around 35 minutes as an idle because we are not back to office also.
Okay. How about others? I can come at 5:15 if it is okay. But is it okay for others?
Yes, sir. Yes, sir. Yes, sir. Absolutely okay, sir.
For everyone, 23 and 24 batch, you don't have any other class?
24 batch, please come back.
Sorry?
For us, if it is little late, it will be 5:30 is good per time for us, sir.
We
Like,
have office constraints, sir. 5:30 is
office,
the
24 batch, 5:30 will be good for us.
better.
So,
Okay. So in order to make the comfortable, so one team has to wait for 30 minutes. Sorry. Because these timings have been arrived by interacting with the people in the beginning of the semester. Yeah?
No issues, sir. We just wanted to inquire. No problem.
Yeah. Thank you. Okay. Bye.
thank you, sir.
Thank you.
Thank you, sir.